have a list of illustrations to prove how short circuit current is limited by using reactors, and I am going to share it with you today on Uni Learning. Friends, in my earlier videos, I have already shown you that in case of symmetrical fault, very large amount of current flows through the system, which is very dangerous, and it may hamper the complete system or may result into complete shutdown of the power system. So to limit the current flowing through the system during short circuit, we are having reactors. So let's solve one numerical how reactor helps to control the short circuit current. Take an example. A generating station is laid out as shown in the figure. So single line diagram is provided here. The ratings and percentage reactance of different elements is indicated. If a three-phase short circuit occurs on any feeder near transformer secondary, fault point F, here fault point F is shown, find the short circuit MVA fed to the fault. So here we have to find out short circuit MVA on any feeder. So here considering this particular location to find out short circuit MVA. To proceed, we are having single line diagram, so no need to draw it separately. The next step is we need to select base kVA or base MVA. So let us choose base MVA. Choose base MVA is equal to 5. I am considering here 5 MVA as a base. You all are well familiar with this selection of base MVA. You can consider either any random value or highest value from this power system, or you can add or sum up all the components together, the ratings of all components together, and that value you can consider as a base MVA. So here for simplicity I am considering base MVA is equal to 5. The next step is converting all reactances of each and all components on common base. So let us start one by one. We will start first with calculation of percentage reactance of each generator. All three generators are of same rating, so we are considering percentage reactance of each generator on the base MVA is equal to, the formula for that, for calculating percentage reactance at base kVA or base MVA is equal to base kVA upon rated kVA into percentage X at rated kVA. So I am going to use this formula here. Apply this formula, you will get base MVA divided by rated MVA into percentage reactance at rated MVA. It is 7.5%. Similarly, you have to go for calculation of percentage reactance of each transformer. All transformers given in the diagram are of same rating. All reactors connected in the system are also of same rating. So it is very simple for calculation. On the base MVA is equal to 5 divided by 5 into 5. So it comes to 5%. Similarly, percentage reactance of each reactor on the base MVA is equal to base MVA 10, 5, rated MVA 10 and rated percentage reactance 10. So it is 5 divided by 10 into 5. So it comes to, it is 5 divided by 10 into 10. So it comes to 5%. So in this way we are having base reactances of all components on common base. So next step is drawing percent reactance diagram for calculating equivalent reactance of the complete system up to fault location. So let's start drawing equivalent reactance diagram of this power system or this generating station. So for your reference, keep this diagram with you. I am going to draw its equivalent reactance diagram. Reactance of generator, reactance of reactor. We are having 2 more generators and 2 more reactors in the system. When fault will occur, this is A, B and C. This is K, L and M. These are the points. Equivalent reactance of each generator is 7.5%. Equivalent reactance of each reactor is 5%. That of transformer which is near to fault location is 5%. So in this way we will get a reactance diagram. This is your reactance diagram. Now by referring this reactance diagram, you have to find out equivalent reactance of the system. So by series parallel combination, you will get that value. These two are in series. Similarly, these two components are in series. So 7.5 plus 5, that is 12.5. So 12.5 and 12.5 of this branch will come in parallel, and finally you will get equivalent of this parallel combination. So let me write here. Seven 7.5 plus 5, that is 12.5. That branch is in parallel. So there are two branches of 12.5. So equivalent reactance of the system, reactance is equal to 12.5 in parallel with 12.5. It comes to 6.25%. So equivalent reactance of the two parallel branches will come to 6.25%. Then 6.25 plus 5%. Now simplified diagram. So your point is your neutral. This is 7.5%. It is 6.25% plus 5%. So now we have to find out equivalent reactance of this particular system up to fault location. So 6.25 plus 5 is 11.5. So 11.5% and 7.5% will come in parallel. So by series parallel combination, equivalent reactance, it is 11.25, reactance of generating station up to fault point it comes to 9.5%. So equivalent reactance percentage xt is equal to 9.5%. So next step is finding short circuit MVA. So what is the formula for that? We are having short circuit MVA is equal to base MVA into 100 divided by percentage fault reactance. So short circuit MVA is equal to base MVA is 5 into 100 divided by fault reactance. Its value is 9.5. So just do the calculation. You will get short circuit MVA is equal to 52.63. This. So just with the help of this tie bar reactor, this is arrangement of tie bar reactor. So with the help of this tie bar reactor, the complete system is getting protected, or you can say short circuit current or short circuit MVA is limited with the help of tie bar reactor system. Thank you.